Are you getting the idea? Sunday? Do you have it in your calendar? You should put it in. Good. All right, so a rundown of all the things that I want you to be doing after class today. If you haven't already, you should do your Module 3 checkpoint. After today, you'll need to do your Module 4 checkpoint. You'll also need to do your Unit 2 checkpoint. That's in addition to the Module 1 checkpoint, the Module 2 checkpoint, and the Unit 1 checkpoint, which you should already be done with because we finished that Monday. And where do you find these? RealChem. So you'll need to go to Canvas, open RealChem, and complete them. Then the grade will populate into Canvas. Okay. You also should have already done your Module 3 pre-reading quiz and your Module 4 pre-reading quiz. So if you haven't done those should have been done before today. But you need to take your Unit 1 to 2 pre-test reflection. I know a handful of you have taken that. Jacob, how many points do you get on that reflection out of 1 point? You get 10 points out of 1 on that reflection. That assignment is a bonus quiz. When you go and take it, I give you 10 out of 1 point, which means 9 points extra credit, and it feeds directly into your unit test category, which currently has nothing in it. So when you get 9 out of 1 point, or 10 out of 1 point, it looks like you have a 900% in that section, or 1,000% in that section. So it's going to bring your grade all the way up until you actually take the unit test, and then it will just operate as bonus points. Take it, because you can't lose points. I mean, I guess maybe you can lose 1 point, but you'll get 9 extra points. Then you should take your practice test. How many times should you take your practice test before the actual test? Take it twice, because you're going to keep the highest score. It cannot hurt you to take the highest, to take it twice. You just have to plan for it. My advice, go through that practice test once. Don't spend 2 hours on it. Spend 30 minutes, 45 minutes, an hour. Once you feel like you're done, see which ones you got right. Mark those off as I'm competent on those concepts. Look at the ones you got wrong. Go back and review your notes. Go back and review RealChem. Study up on those materials. Then come back for your second attempt. You also have your test study guide. I actually forget if you need to upload this or not, but there is at least a calendar reminder. It's not something you upload. There's a calendar reminder that says make a study guide. That's basically kind of your cheat sheet for the exam, but it's not, or for the test, but it's not what you have to use for the test. Then you actually take your test. How many attempts do you get on that? Just 1 attempt. And that's on Lockdown Browser. Your practice test is not on Lockdown Browser. How long do you get on that? 2 hours. Plan for using the full 2 hours if you need it. So in your calendar, you put it for Sunday, you put it for Friday, you put it for Saturday. Block out a 2-hour period if you can to do that. You don't need to spend all that time on the practice test. The practice test actually goes into participation points. So this doesn't have as much of an impact on your grade as the actual test itself. So remember, if you do poorly on the practice test both times, keep studying the concepts you got wrong so that you can improve that score on the actual test. That means if you're planning to take the test Friday, plan to take the practice test twice Thursday so you can study in between. If you're planning to take the test Sunday, take a practice test Friday, take a practice test Saturday, study in between. Saint, you had a question?
Yeah, I was going to ask, for the practice test, do we get participation points for that just for answering the questions, or is it if we get them correct? Did we get
It is if you get them correct.
Thank
But
you.
remember, yeah, that's a good point. It's all, you get the points you get correct towards participation. But what else is in participation? Your pre-reading quizzes, your Feynman notes are in participation, so it gets buffered a lot.
Okay.
So if you don't do well on it, it's not going to impact your grades significantly. Yeah? Then you have a post-test reflection. This is another opportunity for bonus points. This is the only unit test that you get bonus points before and after it. So make sure that you lean into it. Why would you throw away those extra points, right? Take them, claim them, do that test, do a reflection, and don't just do it for the points. Process it. See what those questions are trying to help you learn. Metacognition, right? Think about what you're thinking about. Anything that you guys think I'm missing? Good. So things that you get to use on the lockdown browser. This is Open Notes, which means your study guide, if you make one, is a great resource because that study guide is all the things I'm struggling to remember and summed up examples of all the things we've learned. But you get to have your notebook, whether that's a physical notebook or an electronic notebook. But if you have your notes on your laptop and you need to use your laptop, you're going to have to figure out another way to access your notes because on lockdown browser you can't open anything up. What are you not allowed to have on the unit test?
Wait, you said that if we had our notes on our laptop, though, we can bring it apart and do our exam.
Sure, yeah. If you have access to 2 computers, you can have your notes on a laptop and use the computer. What are you not allowed to access? The internet. Which means your textbook is technically off the table. You can't go back to rely on the textbook to explain things. That's why you want to extract information from the textbook, put it onto a study guide, put it into your notes so that you have them. Can I stop you from using AI to get the right answer? No, because the problem is Lockdown Browser may flag you and say, what are your eyes doing? What are you looking at? Why are you cheating? But you are encouraged to be looking away and flipping through things and cheating by accessing your notes. So I really can't tell if you're actually cheating or if you're using your notes. If you cheat on the unit test and just get an easy way to get the answers, how well are you going to do on the midterm? Not well. And what weighs more to your final grade? The midterm. So set yourself up for success here. Lean into your skills, lean into your resources, know how to answer these questions because they're not going away. Does that sound good? Okay. Clear? Any questions? As you go through this, I encourage you to write down concepts you're struggling with, because you can take those and turn them into your cheat sheet for the midterm. If you start preparing for the midterm a week before, you might forget what was hard on the Unit 1 to 2 test. But if you write down the concepts that were hard on the Unit 1 to 2 test, then you know what to prepare your cheat sheet with before the midterm. Yeah? Cool. All right, any other questions about this weekend? So I want to say the practice test is due tonight, but it does not lock. Does that make sense? It's going to show up on your calendar for tonight, but it does not. The 18th. Okay, it's due tomorrow. The reason I did that is I didn't really expect any of you to take the actual test Thursday, and I wanted to spread out your calendar because I know it's kind of a lot to look at. Yeah? I think even your Unit 2 checkpoint on RealChem I have due tomorrow because I don't totally expect you to do it tonight after class, but I do want you to do it before the test. I am checking, and the practice test is due tomorrow, but it does not lock. So you can access it all weekend long. When does the test lock? Sunday night at 11:59 p.m. So what is the latest that you should start this test? 9:59 p.m. so that you can have your full 2 hours to answer questions. If you start this test at 11 p.m., it locks at 11:59. You get 59 minutes to test. You do not get 2 hours to test if that goes past 11:59 p.m. Does that make sense? Don't start late. Plan for it. Put it in your calendar. Tell your friends and family, goodbye. I'm going to take my test. Don't bring me dinner. I mean, actually, bring me dinner, but don't knock. Or do knock, because they can't text you because you're not on your phone. You know what I mean. Other questions? It's going to go good. Sorry, I get really energetic up here, and I'm raising your blood pressure too. It's going to go well. Take deep breaths. The only thing you can ever control in the moment is your breath. So when you're taking that test and you're like, oh, my brain is blank, take a deep breath, ground yourself, remind yourself that you have learned this, you have studied it, you can answer them. Sing?
I was going to ask, so for module 3 and 4, are you referring to the electronic structure and periodic properties? Is that what you're talking about that we have done by today?
Great question. Why don't I show you what they're called on here. And then I'm going to pull up the periodic table, and we're going to talk about that periodic table.
And what if we have the periodic table like leading to our notes?
That's great.
We can use that on the test.
You can absolutely use the periodic table. I strongly recommend using this periodic table on your unit test and not any other one that you might have accessed, because this is a tool you need to know how to use for the midterm. If you don't practice it now, when are you going to practice using it? So I've handed them out. I have more to hand out. You can write on yours, but you cannot bring yours to the midterm or the final. I mean, you can bring it. They just won't let you bring it in. They're going to give you a clean version of this. They're going to give you this. And as soon as you get in, you can write on the version they give you. So if you have things that like, I want to remember this on the periodic table, and I've got that on my version. In fact, I'm handing these out. I want you guys to draw on this today. We're going to talk about a few things. Anybody need one? And Saint, here's what we're looking at on Real Chem, Atomic Theory and Periodic Table module checkpoint. That's the Unit 2 module checkpoint. And also compounds and chemical formulas. I'm sorry, I misspoke. Atomic Theory and Periodic Table module checkpoint. That's what we're wrapping up today. We spent most of Monday on. Compounds and chemical formulas module checkpoint. That's what we're talking about today. And atoms, molecules, and ions unit checkpoint. That's the Unit 2 checkpoint. Module 3, Module 4, Unit 2. Unit 2 houses Module 3 and 4. Anybody else? Do you have yours? Get them out. We're going to be annotating them a little bit so that you guys can be familiar with them. Okay. Now I know a number of you have already gotten this far. You already know what you're looking at, but I'm gonna take you through it again. We're gonna talk about it together. Why do they call it periodic, and why is it arranged the way that it is? Did you know that you could arrange the elements however you want? In fact, the most obvious way to arrange the elements is just to rank them, by the number of protons in their nucleus and then just keep going on. Why make it a table? Why not just call it a row of elements? The row of elements. It'd be really long. Be hard to put onto a sheet. Okay, well then you can just take a break and go down and go down. But it's not just called the table of elements. It's called the periodic table. If you analyze hydrogen's properties, you'll notice that those properties start to repeat at lithium. What is it about hydrogen and lithium that they have in common? Well, they both often give up one electron and take on a positive one charge. So we can start to put hydrogen and lithium next to each other on the periodic table. Then, as we look at helium and neon, we notice that they also share some properties. They are stable and they don't bond with other atoms. So the properties of these elements are repeating periodically. But then almost every time you continue getting new atoms, you start getting new properties that don't repeat necessarily with the start. So beryllium doesn't have properties similar to hydrogen or helium, but beryllium does have properties that are similar to magnesium. And so they're placed right over each other because both beryllium and magnesium often take on 2+ charges. They give away 2 electrons readily. Same thing with fluorine and chlorine. These atoms often take on a -1 charge. They often make one bond to other atoms. But there's one element on the periodic table who doesn't really have a solid home on the periodic table. Do you guys know who that is? Its properties model one family and also another family. So placing it on one spot of the periodic table is a bit problematic. Any guesses? It's not oxygen. Oxygen really does behave like the rest of its family. Sulfur, selenium. Who? Helium does behave like its family. Helium's family is the noble gases. It behaves very much like it. I've got it up here. It's hydrogen. Hydrogen has 2 properties that it takes on. It takes on a +1 charge, just like that first group. But it also can take on a -1 charge and have one bond, just like the group 7 family. Hydrogen is not group 1 and it's not group 7. It actually kind of models both of them. So there are some periodic tables, not many, that actually place hydrogen here in the middle to indicate that it's not group 1, despite sharing all of their properties, most of their properties, and it's not group 7, despite sharing most of their properties as well. That's the fun part. All right. So these names that we give to these families. Group 1, you'll notice on your periodic table, it actually calls them group 1A. That's because different people have different ideas of how they should be numbered. Did you have a question earlier I missed? Yeah, okay. Group 1A, often called group 1. These are the alkali metals. Keep in mind, hydrogen is not here, despite being drawn in this family. This is group 1, the alkali metals. And their most characteristic property is that they explode when they contact water. And that's because they readily give away their one electron that they have. One electron to give, meaning that they take a +1 charge often. Those are some of their properties. This is group 2. Who knows the name of the group 2 metals? Good. Did you guys get that too? Alkaline earth. Do you notice something about group 1 and group 2 in their names? They sound way too similar. So here's how I remember it. When you name group 1, you're starting the name of group 2, but you stop early because you haven't gotten all the way to group 2. The alkali metals and the alkaline earth metals. Weird, right? But I agree, it's weird. If you have drank water that says they're branded as alkaline water, that means that they've got some of these ions in it, typically probably magnesium and calcium. That's what it gets its name from. I'm going to jump over the B's, and we're going to move on to group 3, which does not really have a common name for us to talk about, but notice it's called group 3A, and you can think of it as group 3. Group 4 contains carbon. I do think that these have a name. I'm not familiar with it. It's not commonly used. A lot of people just refer to it as carbon's family, if anything. Group 5 is called the pnictogens, with that silent P like in pterodactyl. Group 5 is nitrogen's family, so I feel like you can kind of remember pnictogen looks a little bit like nitrogen. Some people don't call this group 5, and they don't call it group 5A. Instead, they count all the way across the periodic table until they get here, which means that this is group 13, 14, and 15. So you may see two different things depending on how somebody is classifying their table. And I do want you to notice we've skipped that big block in the middle. We're coming back to it. Group 6 is called the chalcones. Good luck remembering. Oh, sorry, I spelled it wrong. Chalcone is a compound. Chalcogens. I was going to say good luck remembering that, but I didn't have good luck remembering that. Chalcones is oxygen's family. Some of the common properties here. Group 2 takes on a +2 charge. Group 3 makes 3 bonds. 4, 4 bonds. 5, 3 bonds. 6, 2 bonds. It's a little bit weird. Group 7. Forgot to highlight my group 6. Group 7 or group 17, these are the halogens. You all have probably heard this name before, correct? You've probably heard of halogen bulbs. I don't know what other context you maybe would have heard it in. But those halogen compounds are some of the most familiar to us. HF, hydrofluoric acid. Anybody watch Breaking Bad? He uses hydrogen fluoride to help get rid of something, makes more of a mess. Chlorine, something that you put into your pool, typically not as chlorine, but chlorine as a part of another compound. Bromine, iodine, which is, of course, useful for our metabolism, our thyroid. I think there's something interesting about that series of family. Fluorine, chlorine, bromine, and iodine, rather than being pronounced iodine. It's spelt exactly the same, but it's pronounced different. We don't call it fluorine, chlorine, bromine, and iodine. I think that's because iodine became a part of the colloquial vernacular language during the nuclear age. People needed iodine to help ward off radiation, so it just started getting pronounced in an easy way, and it evolved to stop being pronounced iodine, or fluorine, iodine. It became iodine. I don't know for sure, but it's an interesting theory nonetheless. And then this last family, group 8 or group 18. You guys know this? Noble gases. And why are they so noble? They have a full shell of valence electrons, which we're not covering in this section.
They don't bond with other atoms.
Exactly. They keep to themselves. They don't bond to themselves. They don't bond to other atoms, which is a lie, because things like krypton and xenon will bond to other atoms, but for the most part, they're pretty inert. All right, I want to go back and look at some other properties. Group 2. These take on a +2 charge, which means that they have 2 electrons to give away. That's the most common property of these. Group 3, these make 3 bonds. And I do want you to recognize those are different things I'm saying. Charges versus bonds. Those are distinct. Group 4 likes to make 4 bonds. And this is where things start to tip back the other way. Group 5 prefers to make 3 bonds, or they take on a 3- charge. Some of group 5 is able to make more than 3 bonds, but we're going to talk about that later. One of their most common properties is taking on 3 bonds or taking on a -3 charge. Notice that group 3 doesn't always take on a +3 charge. It can happen. Group 4 doesn't typically take on a charge, but group 5 can take on a charge or a number of bonds. Group 6, 2 bonds. Or what charge do you think it can make? A 2-. Follow the trend. What will the halogens have? How many bonds? 1 bond. What charge? A -1. Very good. So remember I said that hydrogen is an oddball? Hydrogen can take on a +1 charge, can take on a -1 charge, and often makes 1 bond. That's why That's why hydrogen is not an alkali metal, and it's not a halogen. It is neither. It's truly the only element that doesn't really belong to the rest of its family. Noble gases. What charge do they take on? 0 charge. How many bonds do they make? 0 bonds. Mostly. There's always exceptions. All right, coming back to this middle chunk of the periodic table. If you notice it, it looks like this big rectangle that sits here in the middle. These first 2 rows, group 1 and group 2, they can be called the S block of elements. We're going to come back and talk about what S means later. This right-hand square, they can be thought of as the P block of elements. We'll talk about that later. This can be thought of as the D block, and they're known as the transition metals. I'm actually not sure what transition means. But they are distinct from alkali metals and alkaline earth metals. These are transition metals. Many of them are rare earth metals. They're not found common in our crust. And then you've got these bottom two rows, which kind of got cut off. Some periodic tables don't draw those bottom two rows separate from the rest of the table. Some periodic tables extend the S, D, and P blocks to fit this F block in between them. And you get this long periodic table. But these, the lanthanides and the actinides, these are called the inner transition metals. You are going to do very little with their chemistry this semester. They are incredibly rare on Earth. Their properties are not well utilized yet in chemistry. I know that my graduate program, there was a student that was trying to get one of those chemicals in the F block and utilize it for new properties in a material. That's kind of a leading edge in research right now, is what can we do with those elements? Do you have questions on the periodic table, on these groups, on these families? Why do they call them families? Similar properties. They've got similar traits. Just like you look like your family, these behave, look like their families. That's the idea. Deal? Any questions on it?
Are we going to talk about what you mean by bonds?
Yes, we are. But I do want to see if I can show you one of these.
Is there a reason why, like the P and P block or the D and D block?
Why they're called that?
Yeah.
Yes. It has to do with their electrons, and we're going to talk about it in the next unit. That's one of the long periodic tables. Notice that you get S block, group 1, group 2, F block, D block, P block. Color coordinated, right? But of course, they don't ever publish them like that because they're too long and they take up too much space. And again, those F blocks on the bottom, they're not that common. A lot of them have been synthesized in labs, so they just kind of set them aside. There is an activity that you can do with the periodic table that shows how it is one continuous list that just loops all the way around, developing new properties as it goes. I have it on my other courses. I'm going to add it in my announcement this weekend in case any of you are curious about doing it. I did it once because it was just really fun. It is this, oh no, why would I take it off?
Isn't it the 3D one?
ChemTube 3D? No. Oh, why would I do that? I will find it, and I will get it to you, but it is a periodic table activity. Why did I take it off my OChem 1? So you can print this out. Notice that it kind of looks like what we had before, but then on the noble gas side, they're all slanted. Helium is here. Helium is also here. So you print this out and you wrap it around and you glue helium to helium. And then you'll find that hydrogen feeds to helium, helium to lithium, beryllium, boron, and then boron glues over itself. Neon feeds into sodium, aluminum glues onto itself, argon feeds into potassium. So you can start at hydrogen and you can just trace a solid line increasing one proton in the nucleus every time. You don't have to start at the top, left to right, jump down, left to right, jump down left to right. It shows how the periodic table is truly just an incremental increase in protons with repetition in some of their properties. I had a good time making it. You might too. It reminded me of being in kindergarten, arts and crafts stuff. All right, any questions? Great. Let's move on into Module 4. And I will say, Module 4 has a lot to memorize. So this is a good place to get flashcards, a Quizlet, a friend to show you one side while you have to name the other. Get familiar with these. This is also a good place to build a study guide and make space on your cheat sheet. If you're not going to memorize them, I want you to at least be familiar with them. I don't want them to be strangers to you. Here are some of our learning objectives in Module 4. We're going to be able to distinguish types of compounds as being molecular or ionic. We're going to write and read chemical formulas. We're going to be able to describe bonds, like Saint was bringing up earlier. We're also going to do conversions with a new unit, the mole. All right. We said that chemicals are everything, except for energy. And those chemicals are made up of atoms, and those atoms are made up of unique elements, depending on the number of protons, and we represent them using chemical formulas. We say what elements are there with their symbols, and how many are there using numbers. But we can actually represent chemical formulas in two ways. A molecular formula and a structural formula. A molecular formula simply tells you what that molecule has in it, and it condenses it into just one line. So if we think about water, H2O, the molecular formula utilizes chemical symbols, and it utilizes subscripts. Chemical symbol simply tells you what? The element. In other words, the number of protons in the nucleus. The subscript tells you what? How many of those nuclei are present in the molecule. Notice that I put subscripts assumes one. How many oxygen nuclei in water? One. There's only one nucleus. We don't write it. How many hydrogen nuclei in water? Two. We have to explicitly say it. What would be wrong with these? I'm going to do one more. Good idea. Ellie. I'm not using, well, this is a little 2. It's a superscript, though. and not a subscript.
Is that big 2 gets factored into the hydrogen and it gets factored into the oxygen, so now with that you're saying that you have 2 hydrogens and 2 oxygens.
Kind of. This 2 is what we call a coefficient, which I don't know where math picked that word, but I'm assuming means like co-pilot, co-parent, coordinate, coefficient, and I don't know what efficient is getting at here, how efficiently we're communicating. So the coefficient is saying I have 2 of the molecule HO. It is not describing the number of nuclei in the molecule. This is just wrong. It's not saying that there are 2 hydrogens, and it's not saying that the molecule is 1 hydrogen, coefficient 2 oxygen. If anything, those are 2 different molecules then, because coefficients separate molecules from each other. You can't have a molecule with a coefficient inside of it. And this is wrong because it's a superscript. We say that the superscript is either the charge, if it's on the right-hand side, or the nuclear mass, if it's on the left-hand side. So this is just wrong because it's not being used properly. None of these are an appropriate way to write water. Does that sound good? Structural formula also uses chemical symbols. Now you'll notice that I'm drawing some lines between the 2 hydrogens. I'm not using subscripts. And then I've got more information that we're going to talk about later. I've got those dots. No subscripts. But it must have bonds or charges shown explicitly. It's not just telling you the molecule. What is it telling you? How it's structured. Notice that this structure is different than this structure. The bottom structure says there's a hydrogen that is connected by this line to a hydrogen on one side, oxygen on the other. That's not the same structure. That's a different connectivity. Structural formulas show you arrangement. They show you connection. All right, I'm going to put up a couple more examples for us to apply here. Yes?
Are you saying that one down there, the HHO, that was wrong?
It's a structural formula,
Okay.
but it's not water's structural formula.
Okay.
Does that make sense? It does show connection between atoms, but it's not the right connection between atoms.
Got it. Thank you.
Kind of similar to this.
Yes.
There's different ways that you can write it, but there is one right way to write it.
Got it. Thank you.
This is a compound called calcium carbonate. You may know of it. It makes up seashells and also your bones. Which is the correct way to write the chemical formula for calcium carbonate? The far right? What's wrong with the chemical formula on the left? Superscript cannot be used in a chemical formula unless it's denoting a charge, and then that charge must have a symbol, plus or minus, to say whether that charge is positive or negative. What's wrong with the middle one? Coefficient. At the end of a molecule, which means nothing. So this is not an appropriate thing either. So you may not know the chemical formula for calcium carbonate yet, now you do, but you can still distinguish when a chemical formula is written correctly or not. This is the chemical formula for calcium carbonate. Now, calcium carbonate does not have a structural formula that includes these lines. Instead, calcium carbonate is written like this. Oh, hang on. No, I did it right. Good. Oh, I really scared myself. I thought I picked a bad example. What is the difference between the structural formula of water and the structural formula of calcium carbonate? Water has these lines. Calcium carbonate does not. There's another thing I want you to notice. Calcium carbonate has charges. Water does not. Good. That's it. That's what I wanted you to point out. There is another way that you can try to show calcium carbonate, and it is wrong. If you draw Ca to CO3 with a line, that's not an appropriate way of representing its structural formula. So how do we know what is the right way to draw these structural formulas and what is not the right way? That's what we're going to get into. We're going to analyze these molecules, these compounds, and we're going to figure out what distinguishes their properties, what allows them to have bonds, or what allows them to have charges. Before we move on too far, there's one other formula that I want to show, which is the empirical formula. Do you know what empirical means? What does empirical make you think of? Good, but take it back. Don't tell me empirical formula. Okay, yeah, the empirical system. I don't know why I thought that was spelled with an I. So then I think it's a different word. I think the empirical system is different than the empirical formula. But, good connection. You think of the most important. That's what empirical means to you.
Yeah.
The most important. Okay. Anybody else have something that comes to mind when you think of empirical? Empire. That's where I was going, right? Star Wars, right? The Empirical Army, isn't that what it's called? That's what I think of. And what is the emperor, if not the most important person? All hail Palpatine. No, I'm kidding. That's what empirical is trying to get us to. The sole root, the most important part. This is just the lowest ratio of subscripts. Lowest ratio of subscripts. So you all have encountered acetic acid before in your lives. Acetic acid is a chemical that has a chemical formula C2H4O2. That is acetic acid, vinegar. It can be written other ways as well, but that is one way to write it. How can you write the empirical formula of acetic acid? Divide by 2. That gives you CH2O. That's the empirical formula for acetic acid. But guess what? That's not the only compound that has the empirical formula CH2O. Any of you who have been embalmed before know that formaldehyde has a chemical formula CH2O. So what is the empirical formula of formaldehyde? How do you simplify those ratios? You can't. That is already its empirical formula. Formaldehyde and acetic acid and potentially an infinite amount of molecules share empirical formula CH2O. Does that make sense? All compounds have an empirical formula. Some compounds are their empirical formula.
I was gonna ask, why did you divide by 2, and do you always divide by 2 when trying to find the empirical formula?
Not necessarily. Why did I divide by 2? It's common between all of those subscripts. In fact, it's the largest common multiple. Largest common multiple factor. But I am looking for the largest. I'm looking for the largest thing to divide all of these numbers. Yeah? You don't always get down to having ones as your subscripts. Sometimes you do. All right. So those are your formulas. Empirical, not necessarily the most useful piece of information, but sometimes it's the only piece of information that your experiment will give you. And then you have to find out, is that actually the ratio, or do I need to multiply it by some whole number? So we could imagine a chemical that has chemical formula C6H12O6. Never heard of her. Have you? Have you? Really? Haven't you? Somebody has. What is it? Sugar, glucose, or fructose. I think they have the same chemical formula. That's sugar. And what could I divide by here to get the lowest ratio? I can divide by 6, not by 2, because that would give me C3H12H whatever. Yeah, thank you.
Like, don't those other numbers disappear then? Like, what happens if you with like the 6s?
1.
Attach, like, the C?
It becomes 1. What is 6 divided by 6? Not 0. It's 1. Where's the 1? It's assumed. You never write the chemical formula, you never write the subscript 1. If you've ever looked at carbon dioxide's formula, CO2, we don't call it C1O2, correct? We assume that 1 means there's one nucleus of carbon. True or false? Sugar shares an empirical formula with formaldehyde and vinegar. True. Would you have guessed that? The same thing that we use to embalm bodies is the same thing that you put into your pickles to make them taste good, is the same thing that fruits make. What? Don't give me that face. Come on. Vinegar? Okay, I digress. This is not a food class. Pickles are world's best food. Thank you. I tried to make a pickle recently. It did not go well. I was afraid it was rotten instead of fermented, so I threw it away. All right, we're going to talk about 2 types of molecules. We're going to talk about ionic compounds and molecular compounds, things that have ions and things that have bonds in them. Okay? First, let's talk about how ions are formed. if you want to make a cation, can you tell me what charge this has again? Positive. What do you need to do? Can I take an atom, for instance, lithium, which often takes on a +1 charge? Can I take lithium and just give it a proton, a positive charge, so that it is lithium plus? To clarify, I cannot do this. Why? Because that would not be lithium anymore. I'm not adding a positive charge to make lithium plus, because that would have made beryllium plus. I'd be changing my element entirely. Not a good way to do it. What do we do instead? If I can't add positive charges, I must remove electrons. Lithium minus an electron. I'm going to write that as lithium goes to lithium plus an electron. Lithium plus and an electron. What is the net charge on the left-hand side of my chemical arrow? Neutral. What is the net charge on the right-hand side of my chemical arrow? Neutral. I cannot create charge out of nothing. Charge must be balanced. Lithium neutral becomes lithium cation plus an electron. Neutralizes each other. That's how you make an ion. You take something and you take away its electron. This happens most often for our metals. Metals prefer to lose electrons. That's like alkaline earth, and transition metals. They like to give away electrons, take on positive charges. What happens to the atom when an electron goes away? The electromagnetic force says the positive charges in the nucleus are pulling on the negative charges in the electron cloud. What makes up most of the size of the atom? The electron cloud. And now, there's less electrons in that cloud for the same amount of protons. There's a stronger pull on the electron cloud. The atom shrinks. By taking on a positive charge, the atom becomes a smaller size. Good? Anions, negative charges. We could show this as fluoride. Fluorine plus an electron becomes fluoride minus. We could show this another way. We could say oxygen plus 2 electrons becomes O2 minus. What's the net charge on the left-hand side for the fluorine reaction? No. -1. What's the net charge on the right-hand side for the fluorine reaction? -1. Charge is balanced. Net charge for oxygen's reaction? 2 minus. Both sides. Charge is balanced. And you might be asking, with lithium, where does that electron go? And you might be asking, with oxygen, where did those 2 electrons come from? Reactions. Lithium will give away an electron. Fluorine will take it. Oxygen will take 2 of them. I have a question. Why is it 2E and not E subscript 2? Because electrons cannot be compounds. Electrons are not chemicals in and of themselves. You can have 1 electron, you can have 2. You can have 1 electron, you can have 2 electrons. Coefficients. You could have 1 molecule of water, you can have 2 molecules of water. Coefficients. So this is not a chemical. If anything, it'd be electron 2 minus, or E2 2 minus. It doesn't exist, right? Coefficient necessary at this point. Am I clear? 2 as a coefficient there is telling you how many electrons. Similar to how 2 as a subscript in a chemical tells you how many nuclei. But electrons are not chemicals. Electrons are not compounds. They don't have subscripts. Cool? If metals prefer to give away electrons, how do you think we could describe those atoms that prefer to gain electrons? Yeah. If you have a metal, the opposite is a non-metal. What groups on your periodic table are non-metals? Most of groups 3 through 8 are non-metals. But there is this weird staircase. It starts underneath beryllium and it zigzags all the way down through that P block. And we call it the metalloid staircase. You won't have to name the metalloids, but I do want you to be aware of that metalloid staircase. There are P block elements that are metals. They're just not transition metals because they're not in this rectangle. So we say that metallic character and non-metallic character go opposite ways. Metallic character increases as you go down the periodic table and to the left. Non-metallic character, things that prefer to become anions, increases as you go up the periodic table and to the right. Helium is your most non-metallic element. And then we could say that francium is your most metallic element. Here, just talking about this application, gaining and losing electrons. Okay, what happens to the atom when it becomes an anion? It gets bigger. It now has the same number of protons with more electrons that it's trying to pull on. It can't pull on them all quite as well. So now that atom takes up more space. The electrons pull away harder. Okay? All right, why don't we take a quick break? Let's just do 5 minutes, and we're going to come back in to talk about nomenclature. And if you guys don't need 5 minutes, then we'll start earlier than that. But I want you to have a chance to move around and get your blood flowing.
So when you're talking about cations and anions, are you just referring to like the charges that
Yeah.
they have on top?
Anions, cations. But notice that lithium on the left is not an ion. It has no charge. Lithium plus on the right has a charge. So when you look at the periodic table, these aren't necessarily atoms or ions. They're just elements.
Okay.
If lithium has all of its electrons, atom. If it gives up an electron, ion. The +1 charge.
Say that one more time.
If you're looking at your periodic table,
Okay.
when lithium has all of its electrons, atom.
No
After
charge.
it gives up an electron, lithium plus ion.
Okay.
And your periodic table doesn't tell you which it is,
Okay.
but it gives you a hint. Once it becomes an ion, it's +1.
Okay. But
when it doesn't have one atom.
Mm-hmm.
Okay,
Mm-hmm.
thank you.
Welcome.
Professor Flood, I have a question then. You asked us what the charge of fluorine was. You said it was negative, but on the left side, you just said it was neutral. So in the middle is when it's negative, and then the right side.
Neutral, no charge.
Yeah,
Anion, negative charge.
yeah.
There's nothing in the middle.
You said that you asked a question when you said, what's the charge on the left? I'm assuming,
The reaction is net negative because there's one electron.
oh, so you're talking about like fluorine plus the electron.
That's right.
Okay.
What's
I thought you were
the-
just talking about the fluorine.
That's okay. What's the sum of fluorine plus electrons charge? -1. Same thing up here. What's the charge on the left? Neutral. What's the sum of lithium plus an electron's charge? Neutral. That equation is balanced. Cool?
Would we ever be asked to like switch, like, given the empirical formula and like go from the empirical formula to a molecular formula? In this class?
Later in the semester, we're going to come back to that. After we learn more about bonding and we start doing more with experimental techniques,
Okay.
we'll say, here's the empirical formula and here's how much mass the sample had. What is the chemical formula?
Okay.
So not in this test, but you may see, here's a chemical formula, choose the correct empirical formula.
Okay. Yeah, I just don't want to confuse myself, but like I'm still confused on like where the two, like I know we factor them out by taking like the greatest common factor and like dividing all of them by it.
Yeah. Where did the 6 go?
But yeah, like where did they go? It just changes.
How come formaldehyde never changed at all?
It just changes into a 1.
Formaldehyde doesn't
No,
change
I'm
into
talking
a 1.
about sugar. So if you
Yeah.
take 6, right, and you divide it into 12, the 12 goes to a 2, the 6 goes into a 1, because 6 goes into itself 1 time.
That's right.
But
Why don't we write the 1? We don't need to. It's redundant. I have to write the element. Why would I need to say that it's the element just one time? I need to clarify when it's that element multiple times. How would I guess that it's multiple times? I wouldn't. But I don't need to write it if it's just 1. Remember, it's not C1O2, carbon dioxide. It's just CO2. How many carbons? 1. This is not acetic acid's chemical formula. This is not sugar's chemical formula. This is formaldehyde's chemical formula. But it is all 3 of their empirical formula, which is simply the lowest ratio of subscripts. That's it. If I can divide by a common factor, I do. And that is its empirical formula, its smallest ratio. If I told you I have a chemical CH2O, it is not sugar, it is not vinegar. If I tell you I have a chemical with empirical formula CH2O, I can't tell you which of these it is.
okay, we wouldn't be asked to like identify what CH2O would be
No,
in this class.
no. But to take a chemical and determine its empirical formula, yes.
Okay. By taking the biggest number that can go into all of them.
Good.
All of them.
Yep.
Okay. Thank you.
You're welcome. All right. Ionic compounds. As we discussed, compounds. Oh, maybe we didn't discuss this. Compound requires more than one element is present. So ionic compound is a bit redundant because you cannot have an ionic chemical that does not have more than one element. These are held by positive and negative attractions that we call ionic bonds. Ionic compounds are often a metal with a non-metal, but we are going to look at polyatomic ions. What are we saying there? An ion that has many atoms, not just F minus, O2 minus, Li plus, but things like CO3 2 minus, one ion, 2 minus, many atoms, 4 atoms together. Ionic bonds are incredibly strong. Has anybody ever put salt directly onto a pan and tried to melt it like sugar? Good, I wouldn't recommend it. Nothing happens, really. They have melting points. That's what I'm abbreviating here with MP, is melting point. In the hundreds of degrees C, 200, 300, 400 degrees C. And they're electrical conductors in that molten phase. So if you can melt them, they'll transport electricity for you very quickly. In fact, one of the easiest ways to get an ionic compound, also called a salt, to melt, is to pump electricity into it, and that's how you get enough energy to melt it. All right, we're going to look at naming these binary ionic compounds, but we're also going to look at naming polyatomic ionic compounds. So for now, we're just looking at binary. In a name and a chemical formula, it is always written cation, then anion. Always. In the name as it's spoken, in the chemical formula as it's written. Sodium chloride, Na plus, Cl minus, cation, then anion. We often have these two parts of the name. The cation often ends with ium, sodium, potassium, ammonium. And the anion often ends with IDE, but can also be things like ATE or ITE, ate and ite instead of I. Sodium chloride. So for many metals, that ium is built into its name because they often take on positive charges. Sodium, potassium, calcium, magnesium, you don't have to change the name at all. But for anions, you often have to take the suffix of the name and replace it with IDE. Chlorine becomes chloride, sodium chloride. One more time for me.
If there's multiple different chemicals, if there's like 4 chemicals instead of 2, would it be all the cations and then the anions, or how would you list that?
We won't have to deal with naming ionic compounds that have more than one type of anion or cation. You will only have one type of cation, one type of anion. But it is true that otherwise you just name them cation, cation, anion, typically in alphabetical order. But you won't have to do it. So let's find a way to get the chemical symbol, or the chemical formula, excuse me, from a name. Let's work with the chemical magnesium chloride. What is the cation? Magnesium, because it's written first and it ends with EM. Based on your periodic table, what charge does magnesium like? Magnesium is element number 12, group 2, alkaline earth. Magnesium has chemical formula is an ion Mg2+. Based on your periodic table, what charge does chlorine like? 1 minus, Cl minus. Ionic compounds must balance charge. If they don't, they're still ions. By being called a compound, they are meant to be neutral. If I have 1 ion of magnesium and 1 ion of chloride, am I neutral? What charge do I have? +1. So the chemical formula is not MgCl, because that is not balanced. How do we balance them then? Good. I need a second chlorine. Here's 2 ways that you can do it. Students have told me the box method works really well for them. Take your 2 ions and split their charges into a number of boxes. Mg2 plus becomes plus and plus. I'm going to redraw my chlorine. Chlorine minus, minus. I need to align all of the pluses and minuses, which means I need a second chlorine minus. Correct? Now when I write the chemical formula, I simply write it as MgCl subscript 2. Not superscript, not coefficient, not after chlorine, not before. You always put the subscript to denote that element after the element. MgCl2. You got a question on that?
So you're writing the one that you're adding to? I'm not sure why you put the 2 after.
After the chlorine.
So you added,
If I wrote this as Mg2Cl,
that's not right.
that's telling you there are 2 magnesiums.
Yeah.
So the subscript comes after the element. How many magnesiums? 1. How many chlorines? 2. Notice that this is not correct because it does not balance charge.
So you took a charge off of magnesium and gave it to the chlorine?
So that's actually our next method. We can think about that in a little bit. This is just the box method. Magnesium has 2 charges, 2 positive charges. Chlorine only has 1 negative. I will need a second chlorine negative to balance out my charges. That's the box method. If you don't like it, we'll get to the next one.
Let me see the next one.
Let's do the box method for calcium carbonate. How many plus boxes do I need on calcium 2+? By the way, what group is calcium 2+ in? Group 2. 2+, group 2. So plus and plus, minus and minus. How many of each do I need? 1. So the chemical formula for calcium carbonate, CaCO3. Yeah? Carbonate is an ion you'll need to learn, but we'll talk about those polyatomics in a little bit. The other method instead of box is called the crisscross method. So taking these same two examples, if I look at magnesium 2+ and chloride minus, I am not actually changing their charges, but the charge can be written as the other ion's subscript. That will help them balance. If I have 2 chlorines and 1 magnesium, I will balance them out equally. I'm not changing their charges. This doesn't become magnesium -1 and chlorine +2, correct? But I get MgCl2. That, I think, Kristen, is the crisscross method that you were thinking of. But here's a confusing spot. Let's look at it again with calcium carbonate, Ca2+, CO3 2-. What does that give you? Ca2CO3 2. I have to take all of that CO3 and put it in parentheses because I need 2 of that whole unit. That's different than what we had up here. Ionic compounds are written as their empirical compounds. Ionic compounds do not have multiple equivalences of balancing each other out. You just need one equivalence of balance. That's it. So if I see Ca2, CO3, 2, my 2's cancel out, and I do get CaCO3. Ionic compounds are written with their smallest ratio of subscripts, always. Which method do you like more? Crisscross? Anybody like box? Pick the one that works best for you. There is not a wrong method. Either method, you need to be careful about this. Lowest ratio. Either method. Just choose the one that works for you.
I mean, it seems pretty straightforward and like easy just to do in your head. But is there any examples that would be like confusing that you would have to, I guess, do a certain method? Because it seems pretty straightforward. Like
Either method can work pretty well for either of them. Yeah. The box method just maybe takes a little bit more time to draw out those boxes.
or
But
like any certain chemical that like you would actually have to put some thought into. Like these kind of it's pretty straightforward.
Yeah, like I said, either of these methods would actually help you shortcut doing the mental math. The crisscross just helps you figure it out right away. The box method takes some time to draw it, but then once you pair them up, you've got your subscripts. Yeah. All right, I want to look at the getting the name from the formula.
Why did you drop the negative on the CA? So when you did the crisscross, like,
Because subscripts are not charges. Subscripts don't have a plus or minus. Subscripts are whole numbers, but you can derive the subscript from the opposite ion's charge. I get that a lot. Subscripts are not the charges, they're predicted by the opposite ion's charge. Yeah? Getting the name from the compounds works the opposite way. So let's say that we have Br. How many Ks? 1. How many Brs? They're balanced. The name is potassium, but not bromine. I changed the suffix of "ine" to "ide," and I write potassium bromide. If I have a polyatomic ion, I have to know its names. You have to recognize the polyatomic ions, and you have to know their names. We'll talk about them in a second. But then we have these other elements. If we look at FeBr3, what is the charge on Br? Br is a -1. What is the charge on Fe? I have 1 iron ion, I don't know its charge, and I have 3 bromide ions that are each -1. You can figure out by box method what charge 3 plus iron has to be. What is it? What balance is 3 minus? 3 plus 3. But it's not iron bromide, because iron can also be FeBr2. What charge does iron have here? A 2 plus, because there are 2 bromide ions. I have to distinguish iron 3 plus from iron 2 plus. So in the name, we introduce Roman numerals to describe the charge on the metal. This is iron Roman numeral 3 bromide. Am I saying that there are 3 bromines? No. I'm saying that there's a 3 plus on iron. What is this one? Iron 2 bromide. Not because of bromide, but because of iron 2 plus. So why is it that we don't call it potassium 1 bromide? Because those transition metals don't go through this. Or excuse me, only some transition metals get this. And I'm going to tell you which ones need them. Lead, chromium, magnesium, iron, cobalt, copper, mercury, zinc, vanadium. And I shouldn't have even said transition metals, because lead is not a transition metal, neither is tin. No other metal gets these numerals. These metals must always get numerals. If you call it potassium 1 bromide, you lose points. It's not its name. If you call it iron bromide, you lose points. It's not its name. There are constrictions on the language that we use for this naming convention. That's the constriction. Does that make sense? Comfortable with that? I would recommend that you get to know them. Okay, let's talk about polyatomics. you will need to recognize your polyatomic ions. You have to know them. You need to get familiar. Put them on cheat sheets, note cards, quiz yourself with them. These ions are their own thing. They will have multiple atoms in them. You cannot break those atoms up. Rather than finding one atom and trying to say, oh, it's bromide, you need to recognize several atoms and call it bromate. There are families in these, like the chlorate family. ClO minus, ClO2 minus, ClO3 minus, ClO4 minus. And there's a similar family for the bromates and the iodates as well. These two are the parents of the family. The other two have names that derivatize them. ClO3 minus is called chlorate, ATE, not to be confused with chloride, Cl minus. If you have one additional oxygen, we call it perchlorate, similar to peroxide has one additional oxygen. If you can remember perchlorate, perbromate, periodate, you can work your way down the number of oxygens as you go. Perchlorate, chlorate, chlorite, and one less than chlorite, hypochlorite. Hypo meaning cold, less than. Too low of temperature, hypothermia. Too low of oxygens, hypochlorite. There's this very similar family with bromine and with iodine that you should be familiar with despite Real Chem not publishing them. There are some other common ones, and I want you to realize that the ate and ites move in the same way. Ite is always less oxygen than ate. But ate does not mean a specific number of oxygens. Ite does not mean a specific number of oxygens. This is SO4 2 minus, SO3 2 minus, NO3 2 minus, NO2 minus, NO3 minus, NO2 minus. This is sulfate. This is nitrite. What is SO3 2 minus? SO3 2 minus? SO3. Sorry. SO3 2 minus? Sulfate. It's got one less oxygen than sulfate. This is sulfite. Notice that chlorate had 3 oxygens. Chlorite had 1 less. Sulfite has 3 oxygens. It does not tell you the number of oxygens. It just tells you 1 less than 8. This is nitrite, NO2 minus. What is the name of NO3 minus? Nitrate, 1 more oxygen than nitrite. Do you hear what I'm saying? 8 does not mean this many oxygens. 8 means more oxygens than ite. You need to be familiar with nitrate, sulfate, chlorate, and the number of oxygens that they come with, as well as phosphate. They are not a 1-to-1 ratio. There are very few cations that are polyatomic that you need to know. The most common and important one is NH4+. And like I said, cations begin or end with -ium, so this is ammonium. Now, something strange that happens with polyatomic ions, they are indivisible units. If you have multiple of them, you cannot change their chemical formula in order to express that they are there multiple times. So you need to put parentheses around them as a unit and use that parentheses to put subscripts. So let's look at ammonium sulfate. What is the charge on ammonium? +1. Box method. What is the charge of sulfate? -2. How many ammoniums per sulfate? So can I call it N2H8SO4? N2H8 is not NH4. Those are different chemicals. They have different subscripts. So I have to write this as parentheses NH4 2. I don't have 1 ammonium, I have 2. Ammonium is its own thing, so I have to add these parentheses around it to group it off. Could you imagine if that parentheses wasn't there and I just had NH42? That's a lot of hydrogens. SO4. Cool? Very cool. Now I do want to point out that these names have no prefixes. There is no indication to you in the name how many of each ion is present. Why is that? Why don't I call it 2-ammonium sulfate or diammonium sulfate? Because the charges don't change. And you need to know the charges, and the charges will always balance each other out. So just by saying the name of the ions, you can deduce how many ions of each there are. Now we look at molecular compounds.
Hey, John.
Hi, Kristen.
So on polyatomic ions, for the ammonium sulfate, we don't have to balance them. We can just leave them like that.
Oh, I was setting up for the box method, but I never finished my box method. I need a second ammonium to balance 1 sulfate.
Is there any way to know the charge of ammonium, or you
You need
just need to know that?
to know the charge of ammonium. You need to know the charge of sulfate. You need to know the charge of nitrate. You need to know the charge of nitrite. You need to know the charge of bromate, bromite, hypobromite, perbromate. You need to know the charge of hydroxide. You need to know the charge of acetate. Your textbook walks you through these polyatomic ions pretty well. So when you notice a polyatomic ion, you should write it down. Yeah. Okay, molecular compounds as opposed to ionic compounds. These have shared electrons between atoms, not ionic bonds. We call these covalent bonds. We're going to talk more about what valency is later. These can exist in all sorts of phases, not just solids. They have a range of melting points and boiling points, but I want to talk about their nomenclature. Nomenclature, by the way, just means system of naming. Because molecular compounds are not based on ionic charges, there is no way to know how many of each will be present in a molecule. You have to explicitly state it. Notice carbon dioxide versus carbon monoxide. Prefixes used except for one of the first element. Notice that we don't call it monocarbon monoxide and monocarbon dioxide. We drop the mono prefix for the first element. We can't drop it for the second element. What is the chemical formula of carbon dioxide? Actually, let me give some options. Is it 2CO, C2O, CO2, or CO big 2? Dioxide, 2 on the oxygen, subscript 2. Carbon monoxide, chemical formula? CO. That's it. Can you give me the name for this molecule? No, water is not correct.
Dihydrogen monoxide.
Exactly. Dihydrogen monoxide. One of the most deadly chemicals known to man. Everyone that ingests this ends up dying at some point in their life. Scary stuff. Yeah? Who have you known that survived water? Nobody that I know. Everyone I know who's died has ingested dihydrogen monoxide at some point in their life. Scary. If you disagree, I don't know what to tell you. My brother had a science report in high school where he reported the statistics. It's real. We also want to talk about acids. Acids are sources of hydrogen ions. In water, an acid is something that will give H+. And we have two types of acids. We have what we call binary acids, H and something. And the rule is that we give hydro at the start, the start of that other element's name, and then we change its suffix to ic acid. Those of you that are in lab this semester have used this chemical, HCl, not HCI, named hydrochloric acid. How would you name this compound? Hydrogen with sulfur. Should start with hydro. It doesn't need to start with di. Confusing. Hydrosulfuric acid. That's right. It's still binary because it's hydrogen and something, despite there being two hydrogens. It's not like it's hydrogen, oxygen, and something. The other type of acid that we have is called an oxyacid. Remember that family that I just drew on the board? Hypochlorite, perchlorite, hypochlorite, chlorite, chlorate, perchlorate. Those are oxyacids, among others. And oxyacids are named a bit different. Here we take the root, like chlorate, hypochlorite. We take that root and we change the suffix to either ic or us acid. And here's how we differentiate it. If you have bromate, you get bromic. If you have bromite, you have bromus. My high school chemistry teacher told me the most vulgar thing I've ever heard as a high schooler. 8 becomes Ike. Date turns to, well, ick. Sorry, I said that wrong. 8 becomes ick. Date gets the dick. I'm putting that on the internet, so don't sue me. That was my teacher, not me. And you'll never forget it, will you? It's ingrained in there now. Already forgot it. Good for you. So here is a chemical called carbonate. And here is its acid, H2CO3. Carbonate becomes eight turns to ic, carbonic acid. You have this in your blood. It's part of what water and carbon dioxide turn into. Carbonic acid. Listen, I got really far. I had to push us. And the one thing I didn't get us to at the end of Module 4 is the mole. And so I just want to give you this overview quickly. In the same way that a dozen is a unit that represents 12 things, a mole is a way that chemists shorten a number by increasing a unit. This is 6.022 times 10 to the 23rd things. Whether that is atoms, electrons, or molecules as a whole. It can be anything. I can have a dozen cars, a dozen donuts, a dozen teeth. I can have a mole of teeth, a mole of donuts, a mole of cars. Here's a surprising thing about how big that number is. If you take the number of stars in our galaxy. Let's say it's about 10 to the 10. And I try to report it in terms of moles. Well, there are 6.022 times 10 to the 23rd stars in 1 mole of stars. That becomes, I don't know, something less than 1, but I can't really do the math in front of you right now. Let's just approximate and say about 1 times 10 to the negative 13 moles. That is to say, the number of stars in our galaxy does not compare to how many things are in 1 mole. A mole is such an astronomically large number that it actually doesn't fit in an astronomical scale. It's a molecularly large number. Does that make sense? It's a huge number, and it helps us bridge micro scale to macro scale. So do some math. I'll send out examples in my announcement where you can see conversions of macro to micro, grams to the number of atoms you're actually looking at. And I apologize for not getting to do more with you guys, but I've taken you over, and I thank you for your time. Good luck this weekend. Reach out to me with any questions that you have.